Good morning, everyone. Welcome to the IvS seminar. It's the last one this academic year, so we have Michael Abdul-Masih closing the seminar series this academic year for us. He's an external, as you know, but not quite. So Michael has a background from the United States where he did his bachelor's and master thesis, and then he moved to KU Leuven for his PhD, and I think he worked with this weird guy over here with Uk. And after that, he spent like 4 years, I believe, in Chile, enjoying the sun there after rainy Belgium as an ESA fellow. And now he is enjoying the sun even more on Tenerife, even though sometimes suffers from annoying tourists, I believe. Today, Michael is going to talk about FASTWIND models, but in particular how to efficiently emulate those models using deep neural nets. And I'm curious to hear all about it. Michael, the floor is yours.
Yep, thanks. I'll say that going to Chile and now to Tenerife was to escape all of the rain from here. So it's okay, so before I start, I just kind of want to give you guys a little bit of a background about me and who I am and what I do. I recognize some faces, but a lot of you I don't recognize. So my main kind of science topic is massive deformed stars. I'm really interested in stars that are not spherically symmetric. So contact binaries, rapidly rotating systems, semi-detached systems, all of those. And one of the things that I've been really interested in lately is how those deformations from spherical affect the parameters that you measure for them. What I'm going to talk about today has very little to do with this, but that's usually what I'm interested in, and it is related kind of in an auxiliary sense. So we'll come back to that, and a little bit about kind of where my expertise are. I do a lot of binary analysis, both spectroscopy and photometry. I'm on the Phoebe development team. I do disentangling, FASTWIND, SPAMs, which you'll learn about today during the talk. And I was also the X-Shooter instrument fellow while I was at ESO, and doing lots and lots of observations. So if you're curious about any of these things, please feel free to come and talk to me at some point. I'm happy to talk about anything. So, all right, now to what I'm going to talk to you about today. This is a project that I've been working on kind of off and on for a little bit. But I'm finally at the place where I have results and things to show, so I kind of wanted to show you what I've been working on. And that is emulating FASTWIND with deep neural networks, and kind of some applications and some first results. So before we get into this, there are several groups here working on massive stars, but I always think it's important to say why we want to study these stars. So here, when I'm talking about massive stars, I'm talking about stars that are more than 8 times the mass of the sun. These stars have strong UV, strong stellar winds and UV fluxes, and they drive the chemical and mechanical feedback, the chemical and mechanical evolution of their host galaxies. So kind of understanding massive stars, how they live, how they're born, how they evolve, how they die is important to kind of understanding the universe as a whole. So it's important that we understand them. We can't really talk about massive stars without talking about binarity. A majority of massive stars are found in binary systems, and we expect about 70% of these systems to interact with a companion at some point during their lives. And the presence of a second object can really have a large impact on the stellar evolution. So most of my time I spend in this kind of chunk of the triangle of the pie slice. But today I'm going to be kind of talking about this slice, but also some of these other ones as well, and kind of how we can better understand these systems. We also can't forget about rotation. Rotation is also very important in massive stars. Throughout the lives of massive stars, you expect them to rotate quite rapidly at several phases during their evolution. And this rotation is expected to lead to mixing, which can fundamentally alter the evolutionary path. And it can also change the 3D geometry of the star. So this is showing the geometry of a star that's rotating at 0% critical, 70% critical, and at critical rotation. And you can see kind of how the surface geometry alters. So kind of what I'm getting at here is that deviations from spherical symmetry are common throughout the lives of massive stars. However, the way that we usually fit massive stars is in 1D. Now, one of the things that happens when you have these deviations from spherical symmetry is that you have internal mixing, which gets driven by a few different mechanisms in the core. So for example, if you have differential rotation between the core and the envelope, this leads to shear instabilities, which kind of leads to eddies forming between your core and your envelope. When you have the deviations from spherical symmetry, what happens is that you'll have a warmer pole and a cooler equator, and this will drive large-scale circulations within the envelope of the star. So this will allow you to pretty much bring material from your core up to your surface, depending on how efficient the internal mixing is, how rapid the rotation is, and all of that. So how do we actually detect these internal mixing processes? We do this through spectroscopy. We look from the CNO cycle. You would expect your helium abundance to increase as you're burning hydrogen to helium. But some secondary effects is that you would expect your carbon and your oxygen abundance to decrease and your nitrogen abundance to increase, because this is a catalytic cycle and you're kind of converting your oxygen and your carbon into nitrogen. And this also leads to surface temperature changes, and we detect all of this with spectroscopy. So that is the reason why I am interested in studying spectroscopy of massive stars, so that we can better understand these processes. So I'm really interested in these processes specifically. Now, traditionally, the way that we would fit these systems is in 1D. In massive stars, you need to account for NLTE effects, and the computations of those are quite expensive. So as of right now, most of the codes that are available are only in 1D, and I know that there is some work being done here to kind of expand that a little bit into higher dimensions. But yeah, traditionally this is done in 1D. So pretty much if you take your rapidly rotating system, you need to come up with some representative model that looks something like this, but it's spherical, right? So you need to come up with some average surface gravity, some average temperature, etc., some average parameters. And you're approximating your star that looks like this, and here I'm showing the temperature distribution across the surface with something that looks like this. And then, of course, later you'd convolve it with a rotation kernel, and this is how you would fit your system. When you're working with stars that don't rotate too rapidly, this is not a bad approximation, but once you start getting into contact systems, semi-detached systems, rapidly rotating systems, this kind of falls off a little bit. So one of the things that I worked on during my PhD was a way to kind of get around this problem, and we came up with SPAMS, which is a spectroscopic patch model for massive stars. And the way that this works is first, based on the geometry of the system, we create a mesh, a 3D mesh, that represents the geometry. And then we populate the mesh with the local conditions. So here, for example, temperature across the surface. And then we can assign individual line profiles, so individual spectra, to each patch across the surface. And here you can see in the cooler regions, here I'm showing a helium-1 and a helium-2 line. So in the cooler regions, your ionization balance is shifted towards helium-1, whereas when you go to the hotter regions, you have your ionization balance is shifted in the other way. So by assigning spectra to each of these patches across the surface, if we then integrate over the visible surface, then we get line profiles that account for the 3D geometry. And also the rotation, we no longer need to use a rotational kernel to broaden it. Each individual patch across the surface has a local radial velocity, a local surface gravity, a local temperature, etc. So we're using all of those local conditions to kind of construct this. And this doesn't only work for rapidly rotating systems, you can also do it for contact systems, and you can get the line profile, for example, at any given phase, any given configuration that you want, like this. So this is a really powerful tool to actually model these distorted systems. And for example, if you just take the light curve solution that you have for VFTS 352, which is just a contact system that I was showing in the previous slide, and you calculate a SPAMS model and overplot it on top of the observed spectra, you see that we get a very good agreement here. So this wasn't any fitting, I didn't do any fitting, I just took the light curve solution and calculate the model, and you see that it's already quite good. Of course, you can do more fitting here. For example, adjusting the abundances and all of that will give you a better fit. So SPAMS is great. I'll tell you about how great SPAMS is at any time. But I will admit that there are some limitations to the way that SPAMS works. So you need quite a large input grid. You need the models that are pre-calculated so that you can assign them to the individual surface triangles, right? Given the large parameter space, we often need individual tailored grids for each object. So the parameter space is very large. We cover very, if you're looking at two different stars, they may have very different radii, very different temperatures, very different log Gs. Coming up with one grid that covers the entire space is unfeasible. When you're using a grid, it requires interpolation, and it's fast, but it could be faster. So those are kind of the biggest issues that I'm currently seeing with spams. And my idea was, how can we kind of improve this? And this is why I have started to look into neural networks. So this is my initial motivation. So if you can use a neural network to emulate FASTWIND, then you no longer need a grid, right? You have an emulator which will allow you to kind of create a model on the fly. So you no longer need to have a large grid of models saved. You can, at runtime, populate directly from the emulator. If you can emulate FASTWIND, you no longer need to interpolate explicitly. I'll come back to that. I have this explicitly here because neural networks are more of a model that represent your system. It isn't exactly, it's not calculating FASTWIND, but we'll come back to that. So. And also neural networks are vectorized, so it should be faster than the current SPAMS implementation. So this is kind of where I started, and now we can talk about neural networks and kind of what they are, how they work, and kind of the thought process behind them. So when you're approaching a problem using classical programming, for example, you have your data, you have some rules, you put it into your machine, you crank the lever, and then you get out your answers. Machine learning tries to kind of turn this around. So instead of having rules and data and getting out the answers, you have data and you have the answers and you're trying to get out the rules. So to put this in terms that are a little bit kind of less, kind of obscure. For example, if we take the FASTWIND example, you have your stellar parameters as your data, you have your radiative transfer equations as your rules, as well as much more. You put those into FASTWIND and you get out your spectra. Now the neural network approach is you have your stellar parameters, you have your spectra, you put it into your neural network and you get out an emulator that allows you to do this process without needing to calculate these radiative transfer equations explicitly. That's kind of the idea behind this approach. So what exactly is a neural network? How does it work? I'm sure many of you have seen diagrams like this. I'm going to try to break this down and make it in a way that is approachable, because I've always been very intimidated by these things. So the way it works is you have different layers in your deep network. You have your input layer, which represents the parameters that you're passing to the network. So for example, you could have your stellar parameters here. You have some hidden layers that you don't see. They kind of work behind the scenes. They do things back there. Then you have your output layer, which would be what you get out. So in this case, for example, you'd get your spectra out. There are other ways that you can do neural networks and other ways that you can kind of approach this problem. So for example, some people are working on neural networks to do spectral classification. So in that sense, you'd put in a spectrum and you'd get out a spectral classification. And then everything that's happening in here is kind of a model that kind of represents the data in some way. So let's kind of get into this in a little bit more detail. So if we zoom in on this component over here, we have a couple of different components that are going on here, right? So this layer will have some values. Each of these connections you can think of as weights, and then you have another layer over here that also has values. And what pretty much you're doing is you're saying that from this layer, I'm going to do something with the data from this layer to get over to this layer. And really what this value over here is it's some combination of all of the values in the previous layer. So this y1 is your x1 times the weight, so this connection here, plus your x2 times its weight. Then there's some function that's being applied to the values that you get out. that tells you what the value of this y parameter is. What this function is called an activation function. And there are a bunch of different activation functions that you can use depending on the problem that you're approaching. Pretty much all what it is it's a transform of your data. So you get data in, and you want to get an output out. In this case, one of the ones that's most used for regressions, which is the type of problem that we're doing, is ReLU. And pretty much all what this is saying is that take the max of 0 or your x value. Whatever your input is, if it's greater than 0, return that. If it's less than 0, return 0. That's all that it's doing. So essentially, yeah, it's just determining what the output of the neuron will be based on the inputs that it's getting from the weights from the previous layer. There are several that are available. You also see sigmoid quite a lot. And I lied to you before when I said that you only had the values, the weights, and the values. There's actually another parameter in there. It's called the bias. That will allow you to kind of shift where the 0 point is. So you can move this left or right based on that bias, and it kind of says when that specific neuron should activate. So when you say below this value, call it 0, and when you say above this value, call it the value. So that's it. So in the end, you kind of end up with this equation here. You have your y1 equals your x1 times its weight, your x2 plus its weight, plus some bias, which is tied to this layer here. And you put that through your activation function, and you get out your values. So to put this into actual values, to make it a little bit easier to understand, if this neuron has a value of 10, this one, or sorry, a value of 5, this one has a value of 10, and these weights here are those. For example, this 5 times 0.4 gives you 2, 10 times negative 1.2 gives you minus 12. You add them together, you get minus 10. Same thing here, 8.54. And now if you apply your activation function here, we'll say all of the biases are 0 just to make things easier for ourselves. Anything that's below 0 will become 0, and everything that's above 0 will just keep its value. So this kind of, this layer will now have these values. And that's all that the neural network is doing. So you have several layers. Usually you have much more complex layers than this. Here I'm only having 3 neurons per layer. Usually it would be much bigger than this, and usually you'd have several layers. And that's really all that it is to it. So you have your input values, you have some weights, you have some activation functions, you pass it through the network until you get to the end, and you get some values that come out. That's all that it's doing. So, as I mentioned, you start with your input, you have your layers, you can have as many layers as you want, they will do some data transforms. The more complex your problem is, the more complex your network will need to be able to compensate for that, and you'll get out some predictions. Great. Well, that's great, but until you're actually comparing your predictions with, oh yeah, here, you have your stellar parameters and your spectra that come out. Until you're actually comparing your predictions with what you expect it to be, it doesn't really tell you much. So if you take your true spectra, or so if you take FASTWIND, you calculate a whole bunch of models where you know the stellar parameters and you get out your spectra, then what you can do is you can compare the predicted spectra that you get out with the spectra that you know that it should be, and you can do some sort of loss function like a chi-square or something else to get some goodness of fit metric. And then you pass this back here and you adjust these weights until you get a network that has converged to a point where you can accurately reproduce these input spectra. So when you're actually doing machine learning and neural networks and training your neural network, this is the process. You're just putting in your stellar parameters, comparing the output that you get with the spectra, and then changing around these weights until you can get to an optimized solution where either it doesn't get any better and you need to either get a bigger training set or increase the size of or increase the complexity of your network, etc. So, going back to SPAMs, originally what we calculated when we released the first version of SPAMs is we had this kind of input grid. So this is 43,780 total models, we have 199 log G and TEF combinations, and you can see them all here. And then on top of each of these dots, you have 4 helium abundances and 5 CNO abundances, and also 11 radius points. And this is kind of the parameter space that we were covering with SPAMs, which is great, but if you'll notice, for example, our radius points that we're covering is quite constrained. I mean, this will cover the main sequence, but as soon as you get a little bit evolved, you're going to be way outside of that. So this grid is quite a lot of models and is already quite constraining in terms of what you can fit. And this is the biggest grid that we've calculated for SPAM so far. Usually the way that we would do this is if you have a system that doesn't fall on this grid, you'd calculate a little kind of small grid just around the parameter space of where that system is expected to be, and go from there. So the idea with the neural network is to try to kind of expand this parameter space and approach this problem from a different perspective. So we're going to use the same number of models pretty much. We're going to use 50,000 models instead of this 43,780. But the models are going to be randomly distributed. So instead of having a gridded way of organizing the models, it's going to be randomly distributed across the parameter space. Here, for example, we expand our temperature going from 15,000 to 60,000 instead of the 25 to 50 that was in the original grid. Our log Gs are expanded as well, going from 2 to 4.5 as opposed to 3 to 4.3. The radius, we're covering from 5 to 30 solar radii. Helium abundance, we're missing a bracket over there, goes up a little bit. And the CNO abundances we're also expanding just a tiny bit. But what that looks like when you plot all of the models, for example, in log G and TEF space, here are all of those 50,000 models that we are doing. So as you can see, we have a much denser coverage in both log G and TEF. And by computing the models in this sense instead of in a gridded sense, you can have 50,000 different individual temperatures and 50,000 individual log Gs and 50,000 individual radii. So especially for a neural network, when you want to train your network, the more values that it's seeing that are different, the better. So using a fixed grid for training kind of hampers your network a little bit. So by this approach, we are kind of getting the best of every dimension. If we look at it in radius versus log G space, this is what it looks like. And here I just have some stellar evolution tracks plotted just to guide the eye. And again, temperature and radius space, we've made some cuts to kind of avoid areas of the parameter space that we don't necessarily need. And this is kind of what it looks like in the end. So our network is a little bit more complex than the one I showed you before. But now that I explained how all this works, you guys are experts. You can understand this great. So our input layer, we have 6 parameters that we're fitting, or that we're including. We have the temperature, the log G, the radius, the helium abundance, the CNO abundance, and this mu, which is the emergent angle. So pretty much the angle that the ray of light is leaving the surface of the star. We have 4 hidden layers, one that's 64 neurons, and then 3 that are 1024. And then we have our output layer that is 61 neurons long, which is the length of a FASTWIND, the number of wavelength points in a typical FASTWIND output. And again, we're using ReLU activation functions for each of these, and you guys know what that looks like now as well. So how does the performance of FASTWIND work, of this neural network work? So what I've done is I've trained our models, kind of going through here, given the parameters for the 50,000 models that I've computed. I've taken 40,000 of them as the training set, and I've taken 10,000 of them as a test set to validate the performance of the network afterwards. So so it's only seeing 40,000 models when it's doing the training. Then at the end, it has 10,000 models that it hasn't seen before, just to check to see if the training that we've done is able to reproduce new data, or if it's only able to reproduce the data that it's seen before. So that's kind of the goal. And if we calculate the mean absolute error, that's what MAE is, your mean absolute error. So if you take your average absolute error that you have across your parameter space, we're getting 0.00258, which is 0.2% across your parameter space. If you'll notice, here over here I have the error. So what I'm plotting here is the validation set. So this is the data that the emulator has not seen before. What you can see here is that in the bulk of where the parameter of where we expect the stars to be, we have a pretty good error, and you can see that as you start getting to kind of the edges of the parameter space is where you start getting more error or higher error. One kind of thing to mention, and you'll see this in a second, but the neural network, it's not. Some of this accuracy or some of this error is just coming from jitter around the continuum. So if we do a thought experiment and we just convolve this, both the output that we get and the spectra that we're getting out of FASTWIND, if we convolve it with a rotation profile of 30 kilometers per second, just to smooth this a little bit to check how whether or not the equivalent width is preserved, what you can see is it improves a little bit. You don't see it too much, but if I flick back and forth between the two, you can see that it gets a little bit better. So it's a little bit better. But this seems to be saying that the majority of this scatter that's coming from is not just this jitter, but something else. So if we actually look at the spectra, this one has a mean average error of 0.007. You can see that we have a very, very good fit here. This one is a little bit higher at 0.0017, and then this one at 0.0037. And the main source of error that we have is kind of the absolute intensity level for these here. So you see that this one, the neural network is predicting a slightly higher flux than what the real flux that you're getting out of FASTWIND is. It's able to reproduce the lines with higher intensity much better than it is to produce the fainter lines, which is good because the lines with higher or the models with higher intensity are going to be contributing more flux in the end when you actually do the convolution. And another thing to note is that we are able to reproduce all of the features. So it's not that we're getting the features wrong. It's just the absolute flux level is a little bit wrong, and that's because in FASTWIND, and I'll mention that this is in log space. Rather, to do this with spams, we need the absolute intensity for each of these input models, so that we can make sure that the flux distribution of the different spectral features across the surface is properly accounted for. Yes. So, how has this improved spams? So, with the grid, interpolation errors can be up to 1% in certain areas of the parameter space. I'm comparing apples and oranges a little bit here, because here I'm talking about kind of the maximum errors, and here I'm talking about the average errors. But as you can see, we're doing quite well, and our average error across the parameter space is lower than that. But in the parameter space, or in the area of the parameter space where we are most often going to be, the error is even better than this. The size, we need about 1 terabyte of space to host that LMC grid. All 140 lines are 2.5 gigs in total, so that's something that can be portable enough to be on your laptop. I can send it to you, not necessarily in an email, but almost. And the times per spams iteration was 7 seconds per line per time step. And now it's down to 1 second. So we have a seven times speed up just by implementing the neural network. I will mention we can make spams much faster by doing other things. For example, the neural network itself is vectorized. Vectorized is just a fancy way of saying that it's using array operations instead of loops. So we can do more to vectorize spams to make it faster. I will also note that all of the times that I'm showing here are based on CPU computation times, but with neural networks, you can also take advantage of GPUs, which speeds things up quite a bit. But for now, all of the comparisons that I'm doing are CPU on this laptop, actually. So, all right. That's great. SPAMs is better now. But what about all the stars that don't need SPAMs? I mentioned before that SPAMs is great for stars that are distorted from spherical geometry, but there are a lot of massive stars that don't necessarily need that level of attention. So if we come back to this plot again, we have a lot of stars that are effectively single. We also have a lot of stars that are not necessarily rotating fast enough that you need to account for the 3D geometry. So pretty much if your rotation rate is below 50% critical, you can get away with, the 3D effects are going to be minimal. So you can kind of get away with fitting it with spherical models. And if you're in a binary system, but you're far enough apart that you have no tidal or Roche deformations, no ellipsoidal variations, then you may not necessarily need SPAMs to do this. So you should be able to approximate it with spherical models. So let's, this should be the FASTWIND, not SPAMs. This is not SPAMs anymore. This is FASTWIND. So let's do the same thing that we did before, but instead of doing this for the SPAMs input, we're going to do this for FASTWIND. So the only difference is that we have, this should be 5. Yeah, so this should be 5 now. And instead of that mu parameter, we're getting rid of that, and it's just your TEF, your log G, your radius, your helium abundance, and your CNO abundance. We're going to do the same training again, but this time, because we don't care about the flux levels on the surface, we can do this all normalized. This becomes a much easier problem if we don't need to worry about the absolute flux that we have here. So if we show the same plot that I showed you before with the average error across the parameter space, here's now what it looks like. As you can see, with FASTWIND, we're doing it much better. Again, this is just with the test set. So this is showing all data that SPAMs has not seen before. And here we're getting accuracies of below 0.1%, better than 0.1%. And if we convolve with the rotation kernel, it disappears completely. So here we're talking about 0.03% as the average error that we're getting here. So what this means is that now we have an emulator that can very, very accurately reproduce FASTWIND models. Great. What can we do with this? Right? Traditionally, when we're fitting with FASTWIND, one of the ways that a lot of us have approached this fitting is through the use of a genetic algorithm. I'm going to explain this super quickly. It allows for an efficient exploration and convergence to the global minimum. It usually requires a few thousand model evaluations, but the way it works is that pretty much you take your parameters and you put them next to each other as if they're different genes. So pretty much you have this long string of numbers which we call a chromosome. Within that chromosome, you have a bunch of individual numbers which are genes. You can say, okay, these first 3 numbers correspond to the temperature, and these second 3 numbers correspond to the log G, and so forth. And the way that works is that you code all of your parameters onto one long string, and then you can do some combinations based on the fitness of your models. So the models that have the best fit, you would combine some of those to form some offspring that have some combination of the parameters that the parents have. And then you can also have some mutations that will change individual values from one thing to another, or delete a value, etc. So there are ways of doing this. And this allows you to explore your parameter space quite quickly. So we can apply the same thing that we've been doing with SPAMs now with the neural network, with the emulator. So this is a model for this star. It's a random star. I picked it from the Melchior's database, and yeah, you can see that the fit does quite well. We're able to reproduce the spectral lines quite accurately, and we can get out the parameters that we have for the system in the same way that we were doing with FASTWIND before, but now we're doing it with a neural network that is replacing FASTWIND. This whole neural network, or sorry, this whole GA run for 300 generations took 7 minutes on a single core on my laptop. To put that into perspective, when you're using it with FASTWIND, each model will take you about an hour. So if you have a population size of 50 and 300 generations, that would take you about 15,000 hours of computation time. When you're doing it with a neural network, it takes 7.2 minutes, and this is 125,000 times faster speed up doing it with the neural networks as opposed to FASTWIND. So, with this kind of speed up, this really opens up the possibilities of things that we can do. So just for fun over the weekend, I took Melchior's, and I decided to fit every single O-type star, every single single O-type star in the Melchior's database. And we can do some cool things like plotting them on an HR diagram, or not an HR diagram, well, you know, your log G versus TEF, and seeing where they all fall. There's kind of a weird guy over there, which maybe we should look into a little bit more. We can also do things like plotting your helium abundance as a function of your nitrogen abundance, and you can see the correlation. So here you see the CNO cycle kind of working just like that. I used a computer that has 40 cores, and this took 20 minutes to do all of this. So it took me longer to make the plots than it did to actually run the models. So it really opens up kind of the way that we can approach the problem of fitting these massive stars and fitting large data sets, which is going to become very important in the future as we move forward. So to put this into perspective, we could fit the entire X-U sample, which is 250 stars, in an hour, using that same computer that has 40 cores. We could fit the entire VFTS sample, which is 800 stars, in 3.5 hours. Yeah, well, ignoring the binaries. Bloom as well, 929 stars in 4 hours. We could fit the entire ALS catalog, which is all of the known OB stars in the galaxy so far, in about 3 days. So as we move forward and as we start getting to the next generation of instruments that are going to be releasing very high volumes of data, we really need to go in this direction so we can actually get through the data that we're going to be getting out of there. We can also do other things. We can try to fit our stars with MCMC. This is something that we've never really been able to do before because the models take too long to run for it to be feasible. But now we can. With the speed up that we get from the neural net, we can actually try some MCMC. So this is just another random star that I took. Got to the best fit solution, and then I just let MCMC run for a few thousand iterations. We can plot our corner plot, and here you get all of your parameter correlations and all of that for the system. Here's what the fit looks like. It's a pretty good fit. So if you wanted to do a full MCMC run with 16 lines, 10,000 iterations, that would take you about 4 hours to do. So this is also another kind of level of things that we can do with this approach that we were not really able to do in the past. So. No. No. So of course, yeah. No. So I mean, the errors. These are these are purely statistical errors, yeah. No, I don't trust those error bars. But this is the main point here is that we can actually start exploring this, and we can actually start going into this direction a little bit more and improve our fits like that. So all of these things that I've showed you so far, I've packaged up into a Python package. The name is still in progress, so it's a pretty bad name, but we'll come up with something better in the future. But it's just faster neural network fit. This is fine. You know, we'll come up with something better. Everything is kind of packaged up nicely so that you can read in your spectrum. So for example, here you read in the package, you initiate it, you load in your data, you load it into the model, add the lines that you want to fit, then you say, okay, run the GA with 300 generations and 50, your population size is 50, plot the results, and those are the ones that I was showing you. You can plot the fits, those are the other plot that I was showing you. Same thing for MCMC, and you can save all of the results on the pickle. So this is kind of all that you really need to do to make this work. And of course, if you want to customize this more, you can customize each of the parameter ranges, you can customize the line fit ranges that you have and all of that, so it's all available for you to do. I've also set it up in a way that if you have your own custom neural network, you can kind of drop that in using all of the framework that we have there and work with it like that. So this is something that I'm working on and hopefully will be out for the public soon. But all of the plots that you've seen have been generated with this, so it is working. Yeah, I will. Yeah. Yeah, just to summarize everything, using deep neural networks and about 50,000 FASTWIND models, we've created a highly accurate FASTWIND emulator. And we can use these neural networks within the existing fitting framework that we have for these. Within the existing fitting frameworks that we have to drastically increase the speed and drastically increase the amount of stars that we can actually fit with this. And as I mentioned, I really think that these emulators will almost certainly become necessary as the next generation of instruments come online. So, thank you very much for your time.
Thanks, Michael, for an interesting talk. Time for questions, Ook.
Which one?
No, 63, yes. When you read your data, there's no error bars in your data. Is that on purpose?
Yeah, so you can include error bars as well. What I've done here is I've replaced the error bars that you're getting from the instrument with the inverse of the signal to noise. So I'm calculating the noise of the data and using that as the error.
Yeah,
but
so
you can input the.
It's still accounted for somewhere.
Yeah. It's within this function. So if you don't pass it the errors, then it will calculate the error based on the signal to noise. You can also pass it the errors, but usually the errors are too small for my liking. So.
While I have the mic, you have been focusing on 6 parameters because one of the reasons that we started is focusing on CNOs, right, and those abundances. But there are, FastWind can deal with an entire set of parameters focused on stellar winds. Do you have plans to
yes.
expand the method?
Yeah, of course, yeah. So this was more of a proof of concept just to show kind of how this can work and where we can go from here. So I've been talking with Callum, for example, about including wind parameters in there as well. So right now wind is included, but not in a way that you can change any of the parameters. So I can't remember whether we're using the Bjorklund or the Vink mass loss prescription, but we have that using standard parameters. And yeah, in the future we would like to compute a set of models that do include this.
So this is actually attaching on that because I'm sure you talked to Olivier and perhaps Anya. I don't know if Anya is here. Right, no, yeah. We've been doing exactly the same thing, actually, okay, so you should compare some results.
Definitely.
With a master student here. The rest of you should go to our master thesis presentation. But anyway, that's just some more. What essentially we find is that when you include H alpha, you can have some problem because of the winds, right? Yes. So I don't know, do you fit like H alpha, helium-24686 and the wind sensitive lines, or do you discard them?
So yeah, I do find that I have more trouble fitting the wind lines than I do the photospheric lines. So the ones that the one that I showed you was one of the photospheric lines. Right. The wind lines, the average errors are quite a bit higher. So I also have issues right. fitting those.
So your epsilons and stuff, you had like 10 to minus 3, which was good
yes.
on average, but that doesn't include then.
No, that's for an individual line.
That's for an individual. So it's not global. I see.
That's for an individual line.
So
okay. I have separate networks for each individual line of the 140 lines.
Right.
And yeah, so that was the error for 4471, I think.
Okay.
But in general,
have you looked at the H alpha errors?
My H alpha errors are quite a bit higher.
Yeah.
But. Yeah, no, I could get you the exact number.
Yeah,
I'm
no,
happy
no,
to
it's
compare.
okay. I was just curious how you dealt with that, because actually it seems very consistent, because those are the only ones where we have encountered issues. Actually,
Yeah, exactly,
these seem to work really, really well, just like what you have presented. Thanks. Excellent.
Thanks.
Hello. Really nice, cool to see that this is working so well. I had a question, because you said in the beginning you separated in, of course, training and validation set. Did you ever try to fine-tune it based on the validation then and have a third test set to test the validation, or did you figure this as a proof of concept, so like no reason to over-optimize this yet?
So I messed with some of the hyperparameters to try to get, and this is kind of what I ended up with. So with the 3 layers and the 1024 neurons per, I messed with more neurons. I messed with less neurons. I added layers, subtracted layers. This kind of is where I kind of found to be the sweet spot to balance the training time versus the accuracy that I was trying to hit. As far as doing an extra validation, as you were mentioning, I haven't gone in that direction, but yeah.
Out of curiosity, did you see like large variations in the quality of the fits when you added another layer, removed a layer, or was this only marginal?
So it really affected how low my mean average error could get. So I mean, adding extra layers, for example, I could see that it was converging, but the amount of time that it was taking to actually converge was quite a bit longer, and I was already reaching kind of the levels that I was happy with the setup that I had. Reducing layers, I found that it wasn't able to get to the level of accuracy that I was hoping for. So with these I mean for everyone with these kinds of things, it's tuning this is more of an art than a science. There isn't really a right answer, and it's really difficult to kind of know when you have the right setup. You just kind of need to keep testing until you have a result that looks like what you want it to. But yeah, I mean, I'm sure that there could be a better setup with a better, yeah, but I don't know what it is. So.
Last question is, sorry, how did you end up with the number of 50,000? Because that's the thing we've been trying to figure out. Is this also just because it works and then, yeah, I mean, okay.
Yeah, no, my first idea with this is, okay, let me just come up with a nice round number, and I came up with 50,000 also because of space on the computer that I was doing this with. So I mean, those 50,000 models are a few terabytes. Well, so originally I computed this for SPEMs, right? So I mean, we have an extra dimension in there on top of those 50,000. So really, that 50,000 becomes 5 million. It was 5 million-ish models that we had for SPEMs. So yeah, it was just to see how that works at first, and yeah, go from there.
Hi, thank you for the talk. I have a connected question. So I'm wondering whether your second set of stars, which you said don't require SPEMs, need a shallower architecture because you have less parameters. And the second question is, so you mentioned that the main contribution to your error was the flux level in your first set of stars. So I'm wondering, did you see it becoming better or worse as you were experimenting with different architectures, depths, and activation functions?
Yeah, so I'll answer the second question first. With the depths, it's difficult because there are several orders of magnitude that you need to cover. So I'm doing this in log space, and it helps a little bit, but I kind of had to make a decision whether or not I was caring more about the higher fluxes, the ones with the higher fluxes, the ones with the lower fluxes. I think if I expanded the models, if I had a bigger data set, maybe this could help a little bit. But yeah, I did find some variations there, and again, this is kind of what I settled with. Your first question was about yeah, it's possible that I could get away with a smaller network for this one. It's working quite well though at this point, so you know, I didn't feel the need to go to a lower network. But it is true that you could probably get away with it. So it could probably reduce the space contribution or the space size and the computing time by a bit by going to a lower one. It's an experiment that I can do. Yeah.
I have another question that is related to the models this is based on. So what if you figured out that there was one of the assumptions that you made in your models that turns out to be wrong, and you need to improve on that? Does that mean you need to do the entire work again?
Yep.
And also, how do you quantify these errors already? Because I'm sure that there are some assumptions that you put in your models where we really don't know much, like, for example, stellar winds or things like this. We
You're making enemies.
well, it's a very difficult problem. So some people have an entire group working on solving that problem. And that means it's not like we have a very clear solution. So how do you deal with that? And how do you quantify, or like how do you try to put this error kind of in where you know that there is probably some uncertainty because of the physical assumptions?
Sure. So I'm going to completely throw John under the bus here then. No, I mean the whole point here is that we're trying to emulate FASTWIND. So if there are issues with FASTWIND, then we will have those same issues. I mean, the neural network does not have any physics in it, right? It's just a way of representing. It's just a way of having a representation that allows you to get your inputs to your outputs that match FASTWIND as good as possible. So, yeah, of course, if there are issues with FASTWIND, then they will also show up here. And if there's improvements to FASTWIND and we need to run everything again, then yeah, we would need to run it again. So there isn't really too much that the neural network can give you on top of what FASTWIND can already give you. Like it's not going to do better than FASTWIND. It can only do as well as FASTWIND can do.
But can you already put like some error estimates in?
Jan, can we put any error estimates in?
I'm constantly thinking about that, to be honest with you. Hopefully with the 3D models that we're currently working on, we will be able to do that shortly. I would say I would be pretty confident in making the prediction that once we have the neural network solution for FASTWIND up and running, so to speak, so that it's efficiently kind of like exactly what Michael is presenting here, so that is working, we will no longer be dominated by the statistical errors in the fits. We will simply be dominated by the systematics. And then it's about figuring out what those systematics exactly what they have put into place. And the only way we can do that is to let the observational results that we get from these type of models without then significant statistical errors guide us together with the type of higher dimensional models that we are working on to inform what those systematics will be. That's the way I see it go.
I agree, and kind of, I didn't mention this, but I mean, I think this is a good time to mention it. To actually calculate your neural network to get everything working from nothing to having your end neural network with everything trained is something like 4 full GA runs using FASTWIND as it traditionally is. So. You can, if you need to rerun this again with 50,000 models, if you have the computing resources, it's doable. It's not comfortable, but it's doable. You can do it. So I wouldn't be too concerned about having to redo this from scratch again. Once the framework is in place for actually calculating the models and training the network, then you can expand the grid as you'd like. Expand the sample as you'd like, or if new physics comes out, then you can recalculate and do it that way. So, and of course, you can also train different networks that are more tuned towards specific purposes. So, like, for example, if you're more interested in the winds and you want to include all of the wind parameters, that's something that you can do. But yeah, of course, that would require a separate network than what we've trained here. So.
Hey, I just had a question about the methodology. So, okay, so you've done your test data. I guess this is almost a general AI question, but so if you compare the distribution of the test data errors with the training set errors, is this a good way of seeing how much you're sampling? For example, how much potential gain you could get by increasing your sampling, or how much, like min to max for like different stars and so on. You could be biasing your model just, again, from the sampling itself. So like, for example, you've quoted just like the mean for the test data. Would you, I don't know if you actually looked at it or not, but if you took the mean for the same experiment, you just do the recovery again, but for the training data, I guess I might expect that to be smaller. So is it interesting how much smaller, and also how much spread you get, say the standard deviation of that distribution also?
Yeah, sure. So I mean, you want them to be similar.
Okay.
If they are drastically different, like if your test set is drastically worse than your training set, then that means that you're overfitting. So that means that your network is learning too well the data that it has, and that it's not able to predict things that it hasn't seen before properly. So in that sense, if you find that they're drastically different, then that does tell you that your fit is or that your network is kind of overfit, and that may tell you that you have too many parameters, that your network is too complex for the problem that you have, and that may be telling you that you should kind of make it a little bit simpler or something like that. But if you want them to kind of be similar, that way the data that it has seen and the data that it hasn't seen, it's able to fit them equally well, and that means that it's kind of trained well on the parameter space that you have. So, yeah, no, it is valuable to do that, and I will say that, I mean, ours, we have, in most cases they're fairly similar, in some cases slightly higher for the test set, but not so much so that it's super concerning.
Okay, so it's more about, for example, the tuning of the model. So it wouldn't necessarily imply that if they are different, the solution probably isn't to sample better your data set. The solution is probably to, I don't know, add more layers. You can solve it through hyperparameters instead of increased data sampling. Is that a true-ish statement some of the time?
Some of the time.
Some of the time, cool.
No, I mean, of course, I mean, if you have a bigger sample, then that obviously helps. Yeah, but sometimes you can adjust the hyperparameters and get a better model. So.
All right, we are at the hour. Let's thank Michael again. And thank you guys for the great attendance during the whole academic year, and I guess we'll see each other back in this room in the upcoming academic year. Thank you.